recording. And that's just our schedule. If you're watching the recording, we'll meet only online. That's right. If you watch the recording, you don't care that we're not meeting in person. And then you'll have your final exam. It's due by the 1st. It will open up the Saturday beforehand because you don't have a full week here. Like most of our stuff is due on Sundays. Final's going to end earlier because the semester's over. And that's that. And then we're going into chapter 10, which is all about geometry. We'll do 10.1, 10.2, and 10.3. And 10.1 is all about like the different parts. So there's a lot of definitions, there's a lot of notation, talking about like overlaps and intersections and how you name things like that. There's actually different types of geometry. We're talking about Euclidean geometry. There's non-Euclidean geometry, which is like super trippy and bendy and fun stuff like that. That was one of my favorite classes that I took. I really like non-Euclidean geometry. The Euclidean geometry is the only type that you've probably ever seen. There's a straight line, and a straight line doesn't have a curve, and they go infinite in both directions, and you get those segments by like basically stopping a line short where you put an endpoint on both ends. Another very important postulate for Euclidean geometry is that you only have one type of parallel line. So you can have infinite parallel lines, but they all are going the same direction. Where in non-Euclidean, you can have all kinds of strange things happen with parallel lines. The shapes, the parts, the different ways that you can put these things together are what we have on the screen. It's not terribly different in other types of geometries. You have a point which is just a single spot in space. It actually, so it looks like it has like a width to it. It doesn't. You could think of like if you put like a pinpoint, if you poke something with a needle, does that have a length, like a width? I mean, technically yes, but no, right? You can't measure it. So a point is just a spot in space. It doesn't have a length, a width, or anything like that. You name it with a capital letter, just a single capital letter. If you have 2 points in space and you connect them and you stop at them, then that's going to be a line segment from A to B. Now, technically, there's an infinite number of points that make up that segment, but we're not getting into the down and dirty of geometry here. You label it with the 2 endpoints, and then you could see up on top, let me get a little bit bigger here. There we go. That it's just a line up on the top. So you go A to B, you have 2 endpoints, so you have something that looks like this. If one of them keeps going on forever and just kind of like blasts right through, then that's a ray. And the ray ordering matters. So like this is point A and that's all it is. It only gets 1 letter. The line segment AB, I also could have said BA. That's fine. Same thing, both directions, both endpoints. But with rays, direction matter because I'm starting at A and then I'm going through B. So I couldn't say BA here with this line. If I said BA, I'd have to write something like that. So it knows that I start at A and the line goes through B, right? Because you can see here it's got the endpoint at A, and then it on the B side, that's where the little arrow goes. So just be careful about the ordering of your rays, right? And you can see here, this is going to be the other way underneath, where I start at B and then I go to A that way. And you could have said BA if you wrote it like that. So the little endpoints, the symbols got to match. If it's a line, then it extends infinitely in both directions. Then again, you can write it in any form. You use, usually if you're using points anyway, then you use 2, and then this would be line. You see how it's got the 2 arrows? I could have said BA because they both match. It doesn't, the order won't matter there. You can also name lines with like numbers, like I could say 1, and then this would be like line 1. You'll see that also, especially when things have lots of points. So it could be line 1, line 2. These are not nearly as popular where you kind of have these segments with an open endpoint. So if something's open, it means it kind of like starts there, but it's not included. So this A right here is on that line. It's on the segment. This is not included. It's like a hole in the wall. It's like a door, right? Like, is a door part of your room? I mean, like, kinda, but it's an empty spot, right? Like, so you can think about this as this is the door to the room. It's kind of included in the room, but it's more of how you get through to the room. So there's like a little hole. And so it's not included in the set because it's not actually on anything. It's just kind of where that entry point is. And then that has the same rules. So these and these have the same rules with the order going back and forth. So you got rays, you got lines, you got points, you got line segments. That's basically it, right? That's how we make all of these different things. There is a question, the very first question actually in 10.1 talks about plotting points on a grid, which I thought was unusual. So I don't know if course has changed over time or something like that, because I don't see a lot of this. If I have something where I'm talking about a plane, we'll talk a little bit more about planes in a minute, then I have to give you 2 spots. I can't just say point A or point 1 because I have a height, I have an up and a down, and I have a left and a right. So I have to say like how far left, how far right, how, you know, or how far up or down. And so you'll get 2 points, you'll get 2 coordinates for that point. And they're always given the same way, X first and then Y. So your X axis goes left and right, and then your Y goes up and down. And I remember from this, right, like your little Y, you scoop, so that goes up and down. There's not really a special order where you have to do it this way. I just think it's easier if you plot the X first, you go to that on the X axis first, and then you go up or down to the Y. So if I was going to plot 2, 4, and this was going to be point number 1, right? I would go to the 2 on the X axis. So I'm over here. I know it's a little hard to see where I am. So I would say like over to this. And then I say, oh, what's the next one? 4, that's positive. So then I go up to the 4 and I make a point and I label it. And that's it. So -2, 1, I would say, oh, go to -2, and then, oh, I got to go up. That's point 2. I'm going to skip to 5 for a second because 5 says go to -1. All right, so here's -1, and then go down to -5. So I walk all the way down and make a little, and that's point 5. Now, when you have the zeros, that means you're sitting right on the axis. So 0 for the X and Y are in the same spot. So go to the 0 on the X and then go down 3 units. So that's my point 3. And then this one says go to the 5 on the X, but don't go up or down. No up or down. So right here, no height. And so that would be spot number 4. And so on here, let me see if I think I still have this up, just because it caught me by surprise. It's not normally, I haven't found my OpenMath to be terribly interactive. But you could just, like 2, 5, I would go to -2, go to -2. Don't touch it though, all the way. And then go up to the 5. And when you click on it, it just makes the dot. So like 4, 2, and then we'll just do it. So you can go down the list and plot all those points and check it that way. And if something goes wrong, you can clear it. I just found that unusual. That was something that I hadn't really seen on there yet, where you could actually interact with a graph. When we're naming, if you have a bunch of points on a line, then those points are collinear, and that you can talk about pieces of the line or parts of the line. And so the way that you name them matters. Basically, that's like the name of the game in geometry. The notation matters. How you name it matters. It will tell you the type, and sometimes it tells you the direction. So if I want to talk about segment DE, that's this. So I have to use this little line up on the top, and I have to put these two little endpoints here. If I just put a bar, it's kind of like it's incomplete. It's like, did you just forget to put the endpoints? It's really supposed to go all the way to the edges and you didn't feel like writing anything. And the only points that I have labeled on this segment is DE. Now I could have something else in here like H, and then H would be collinear to segment DE, but that's not there. If I want to talk about the line DF, that would scoot through D and F, and then I have to put this line here and then put the edges on here. Now E is on this line, unlike this one where F wasn't on segment DE. It stopped too soon. But for the line, E is on the line DF. I also could have called this line DE. That's fine because it's going to blast right through. I could have said FE or FD, or, you know, like all of those are fine because it's going to extend infinitely out. If I want to talk about array and I want to know FD, that means that you have to start at F and head towards D. So here's my endpoint, and it scoops up everybody else, and I have my line there. E is actually on this one as well. But that's just the nature of where things laid. If I wanted Ray EF, then it would have started here, and F wouldn't have been on that because it would have not started far enough back. So you just have to think about where those pieces are and making sure everything is defined the right way and using the right pieces up on the top. So I think on this one here, it says like which one's a line, which one's a ray, stuff like that. Are there any half lines or half segments? I don't see any open dots. So nothing on here is a half. That's not common. But this has two arrows, and so does this one. So those are both lines, where this is only going to be a ray. So A and B is a ray, and it starts at A and goes to B. So I would have to say something like, oops, not that. A, B, like that. Because if I wrote it backwards, then my ray would be shooting in the wrong direction from here. So you just have to check out all of those different pieces. If you have a couple of lines together, a couple of things could happen. They can be parallel lines, right? We were talking about parallel lines before. So parallel lines, and you can see that they use that notation where the L1 and the L2 are two lines that never intersect. So they're going the same direction at the same speed. If you remember any geometry, like these are lines with the same slope, going the same direction at the same rate, and they're never going to intersect. The distance between them always stays the same because they're always going. This is like you're trying to get around somebody on a highway and you're going the same speed, you know, and hopefully nobody crosses over and you're in parallel lines. They could intersect, and they could intersect in a special way where it's perpendicular and creates a 90-degree angle. 90-degree angles, you see this little box down here, it's hard to see. If you put a little box, that doesn't look like a very good little square there, but that means that that angle is 90 degrees. So if I did something like this, even though it doesn't look very good, if I slap that in there, that means, oh, that's a 90-degree angle. The sign for perpendicular is an upside down T, like this, right? Because you can kind of go boop, like that. Parallel lines is just those double L looking things, because you can remember from parallel or from your lanes on the highway. So perpendicular lines are two intersecting lines that make 90-degree angles. Parallel lines don't intersect at all. Or you can have where the lines intersect and they do something else. Not 90, but they intersect. And then a bunch of interesting things could happen. All right, so let me see if I can find a set of two lines here. Of course not. So we get some pairs. We'll talk more about pairs in a minute. I guess they want to do that. in a different order. I would have did it here. But I do what they tell me. So let's say I have some things that are overlapping, maybe. Then I could talk about unions and intersections. I will say that unions and intersections for geometry is unusual. This is normally stuff you talk about like in set theory type things. Like you have a bunch of answers to one set and answers to another set, and you're looking for overlap, like Venn diagram type stuff, logic type stuff. A union is when everything comes all together. So if you're in one, you're in both, right? So union, and you can remember it with a U, is when all of these things, it's like you're in one and then you just all unite. So they have A there. Let's say I had B, I'll make it small, where it's like 5 and 10, let's say. Then the union of A and B would just be all of those numbers. So A union B would just be 1, 2, 2, 1, 3, 5, 7, 9, and 10, because 10's in this one. Now 5's in both of them, you don't have to write it twice. It's like being a member of 2 different clubs. The intersection is the thing that pops up in both. So that's your in both. So you can think about an and, right, for the upside down U. So I'm in this one and in that one. And the only one that's in A and B is 5. So intersection, you're in both. Union, as long as you're in one, you get to be in both. So if I have something like this, I have these 2 rays. I have ray BD. How can I write this? Let's do this. No, draw. Use this. I have ray BD that's going this way. And then draw. Let's do different. Let's go pink. And I got CA going this way. And I want to find the intersection for this. So what, this is intersection, I think, and. So what points, or what is the solution? What section of those 2 rays are in both? Well, where the double highlighting is, right here. Segment BC. That's in both of them. So point B is in both. I could also say, maybe, I don't know how they want it. Do they want like points B and D, or B and C? Those are in both. For the union, I got A, B. Let's get this out of here. Let's see. Draw A, B. Oh, and that's a segment. And then AD, which is a different segment. Go back to yellow, which is all of this. So what is the union of those? So if you're a member of one club, you're in the member of all of them. Let's say home. No, what am I looking for? Draw. So all of these points would be in here. If they want me to give the answer as points, I would A, B, C, and D. But I think maybe since we're talking about segments, they want it as a segment AD, since I'm going to be able to scoop up all of it. Yeah, they want it written as the collection, not the list of the points. Depending on what the prompt is, either one could be considered correct. It depends on what the prompt is. Like I said, it's kind of an odd thing for geometry to talk about that. Questions so far? Anything you want me to go back to? You know, it's the end of the semester. Everybody's very quiet. If you take your line and you intersect it with another line, you can kind of, if you think about, you know, those old fans, or like when you were in kindergarten, if you like made fans by folding paper over and it kind of looked flat, and then you went accordioned it out and it was like, psh, that's a plane. So I could take that line and kind of like drag it and create this surface area, and that is a plane. Planes go infinitely in both directions. Like it's kind of like a point that got stretched out, so there's no length, there's no thickness to it. It's kind of like tissue paper, like an infinite piece of tissue paper. And just like you could intersect lines, you could intersect planes or not intersect planes. Um, Three-dimensional space gets pretty exciting if you have those planes going the up and down, and then you have a Z. You do a little bit of that in a geometry course. It usually doesn't come back to haunt you for quite some time. Let's look at this question in here, because I know there's something about a plane down at the bottom. I know I saw something about a plane. Ooh, you got a fly in the class. I thought I saw a plane. Maybe it is in another, popped up in another homework. I'll have to check. I know I saw it because that's why I didn't delete it, because I was like, ugh, guess I got to talk about planes. So they intersect just like lines, and the lines we saw, they can intersect. They could be at a perfect 90-degree angle. They could be not intersecting at all, or they can do all the other things in between, of which there's a lot, and that's where you get these pairs of angles. You could have 1 pair, 2 pairs, 8 pairs, could be a lot of different pairs. The way you talk about angles also requires pretty precise notation, depending on how many angles you got floating around. You can talk about angles, well, you classify angles by their measurement, but you can give a measurement, but you can also give like a range. So if I say, oh, it's this type of angle, then I know this. Like if I know it's 90-degree angle, I know it's a right angle. So I could say, oh, it's 90 degrees, or I can say it's a right angle. You can also measure them a couple of different ways. You can talk about radians, or you can talk about degrees. I don't think we talk about radians in anything, I hope, but a radian is the number, if you take a circle and then you take that radius, right? It is how many times you could wrap the radius around the circle. Always. So you always need 3.1415 pi, right, radians to get around half of a circle. So that's why area has 2 pi. If you want to convert between radians and degrees, you just multiply by pi radians, which is usually rad, and then over the 180. Whatever you want to go to, that's the number that's on top. So if you have radians and you want to go to degrees, you put 180 degrees on top. Everyday world, real life stuff, you're going to see degrees. Math stuff, you're sitting in a math class, you're doing applications, you're probably using radians. It's kind of like Fahrenheit and Celsius, and like in a science class, you're probably talking about Kelvin, maybe Celsius. Out in the real world, here, we're talking about Fahrenheit. If I want to name the angle, like give it like a letter name, you got a couple of different options. If there's only like one angle floating around, like this one here, then I could just use the vertex. The vertex is where these two rays come together. So here's ray AB, or I should say BA, and here's ray BC. I link them together at the vertex, so they have the same endpoint, they share the same vertex. And then think about this as like a door, like if this was a door that you can swing, to change this angle measurement in between here. There's only one angle, so I could say angle B. But if there was a lot of angles floating around, and like if I had something that looked like this, well, which angle B are you talking about? This one, this one, this one, this one like this one like that, right? So then you got to use the rest of the pieces of that puzzle to name it. The only rule really is that the vertex has to go in the middle. So you have to say A, B, C, or C, B, A. You can't say A, C, B, because A, C, B would look like that. where that meat part of the sandwich, that's always your vertex in the middle there. So you can name it just with the vertex if there's only one. If you got a lot of angles floating around, you have to put the other pieces for the rays on either side. But which one comes first doesn't matter. If I start gluing together angles, like I kind of did here, like let's make this D, then I have, not only do I have these two rays that share an endpoint, what I've created is two angles that share a ray, right? Because I got this piece here and then I have this piece over here. And when you share a ray, or multiple angles share rays, you got a few things that could happen. You can have where, let me go back to something like this, where they're just two adjacent angles. You can have that these two angles, or 3 or 4, that they all stick together and they add up to 90 degrees. So they make a right angle on the outside here. Like this piece right here. This is 90. I'm going to jump down. It could be that they may add up to 180. Or it could be that they're not actually two rays, that they're two lines, and then you have these two sets of angles. They're kind of like bow ties, like this. Now, these angles could be equal, like these could be equal, like 1 and 2 can have the same measure. Here, all 3 of them could have the same measure. Here, these 2 can have, or 4 could have the same measure. Maybe. It depends on what the measure is because there's a cap. So if you have something called a straight angle, that's 180 degrees. So that's opening the door the whole way up. If you think about a circle, and I'm starting here and I'm opening this angle up, then I have 180 degrees. I can stop, whoops, that's a terrible circle. Part of the way at 90 degrees, where I have that top quarter. Or I can kind of stop in between that 90, here's the 90, and that's called an acute angle, so that's an angle less than 90 degrees. This is equal to 90 degrees. This is greater than 90 degrees, but less than 180, because this is equal to 90 degrees, 180 degrees. All right, so you can have all the way open, halfway open, less than halfway, more than halfway, but not all the way. There's also, you can go past the the 180, and you can actually loop around the 360 a couple of times. We're not going to worry about those. All right, so it's either between 0 and 89.9999, so up to 90, exactly 90, greater than 90, but less than 180, or exactly 180. So those are those kind of groupings. And depending on which ones you're working with, yeah, maybe all 4 are acute, but all 4 aren't going to be obtuse if they're like that, because I need them to add up to this 180, and then one can't be that big. But if they add up to 180, they're called supplementary. Complementary if it's 90. We don't, anything else we don't care. If it adds up to like 68, you don't care about that. You're just adjacent angles. The vertical angles are a little interesting. We'll see them more in a second if we have a third line kind of enter the party. But let's look at supplementary first. So normally for these types of things, it will say something in here like, oh, you know that it's supplementary. You really can't, in geometry, believe your eyes. You'll see a lot of not drawn to scale. So somewhere in that question, hopefully it will say, we know that this is a line right here, like this is L1. So that you know that this whole piece has to add up to 180. And then we want to find these individual pieces. Well, I know if I add this one over here and this one, if I have a straight line, a straight angle, that's got to add up to 180 degrees. So if I add this angle plus this angle, That's got to equal to a 180. So now we got to remember how to solve equations. So when you're solving equations, and we're not going to do any like really crazy stuff, we're probably not going to have a bunch of stuff outside of the parentheses like a 2 or anything like that. If there is, then you multiply it through. If there's nothing there, it's like a little invisible 1. So 1 times a 3x is just a 3x. And 1 times a -7 is a -7. Same thing here where this is a +1, so this would just be a 5x, and that's a +2. Basically just taking off in geometry, because we're not going to be talking about subtraction, taking off your parentheses. We're only going to do pretty simple equations. Once you have this, you need to gather up like terms. Like terms are things that have the same extensions. So if you have an x, all the x's are considered like terms. So 3x and 5x. Oh, I got 3 x's and then 5 more x's, so that's 8x. Yeah.
Shouldn't it be 32x?
Oh, 32. I wrote a 3. Yes, that would have really changed our storyline. It should be 32. So let's get that written down in there the right way. I only saw the 3. There we go. 32, 32. So how about 32x plus a 5x? That's going to give me 37x. There we go. 37x. And now I have a -7 and a +2. So if you owe somebody $7 and then you pay them off $2, you still owe them $5. So that's a -5. And if it's been a while since you've dealt with any integers, you can kind of think about it as when you're adding, if you have the -7 here on the number line, number 6, 5, 4, right? Start with that first number, and if you're adding a positive, you take 2 away from this way. If you're adding a negative, then you take 2 away from the other way. So if it was like -7, oops, and I wrote a 5, and plus a -2, like you borrowed $7 and then another $2, then you would say 2 to the left. Now this is equal to 180. So now what we've done is we grouped like terms. Now we got a 2-step equation. The way you deal with 2-step equations is that you are going to deal with the thing without the variable first. The variable is going to be always the last thing that you deal with. So I have this 5. I need to fill in this hole. Like if it's a negative, I need to fill in the hole. If I have too many, it's a positive, I kind of need to take it off to keep the balance. So if I want to fill in this hole here, that's a +5, which means I got to do +5 over there. That adds to 0. So now I got a 37x equal to 185. All right, if you're subtracting, you add to both sides. If you're adding, you subtract from both sides. I have 37 x's. I only want 1x. I only need 1x. So now I'm going to divide off the other 37. So then when I divide, I get a 1. This is multiplication when it's right on top. So the last thing we're going to pretty much always do is divide. If it said x divided by 2, then yeah, you would multiply. Because if you're dividing, you undo it with multiplication. And if you're multiplying, we undo it with that division. I don't know what 185 divided by 37 is. Let's find out. 185 divided by 37, 5. So x is 5, which sounds great, but you're not done. X is 5. None of these things are labeled just an x. I need to take this x, if I can find my drawer, and say, well, 5 times x, or 5 x's, plus 2. So that's 5 times 5 plus 2. That's 25 plus 2, 27. 32 x's, where x is 5, 160 minus 160, yep, 160 minus 7 to 153. Do these two things add up to 180? Yes. So that means, hopefully, everything else is done the right way. So you can check those out. And so those are the steps, right? You have these two that you're going to add together. We know it's equal to 180 because somewhere in there they're going to say, oh, this is a line, or these are supplementary, or something like that. You combine like terms. Then we're going to add 5 to both sides because if it's subtract, if I want to kind of fill that in that hole, I have to add 5 to keep the balance. I got to do it on the other side. 37x, I only want 1, so I divide off the others. So divide by 37 to get a 1. Got to do it on the other side as well. And then now you got those values, you plug them in. It's the same thing with complementary. It could just be 2. It could be 4, it could be 3, it could be whatever, but you're going to do the same thing. We know because of this little box right here that this adds up to 90. So if you see a little box on there, they did tell you what's going on. That's a 90-degree angle. These adjacent angles where I have these two are adjacent and these two are adjacent. 7x minus 5 and 9x minus 5 are not adjacent. They don't share a ray. Well, let me label it like this. 1 and 2 are, and 2 and 3 are, because 2 and 3 share this one. 1 and 2 share that one. But all of them are glued together at whatever this magic endpoint is here. And if I add these three things together, 9x minus 5 plus 4x plus a 7x minus 5, this all has to add up to 90. So you write it all, adding it up. Combine like terms. That's the next step. So we're going to write it. Write your equation. Combine like terms. CLT, combine like terms. All my x's come together. 9x plus a 4x, that's 13x, plus another 7x's, that's 20x. Then I got negative 5 and another negative 5. So that's a negative 10. That's equal to 90. Then you're going to do your addition or subtraction. How do you know which one? If it's a negative, you're going to add to both sides. If it's a positive, it says minus 10, so you add 10 to both sides. If it had said plus 10, we would have subtracted 10 from both sides. That gives you a 0 there. This is going to go up to 100. The last thing is going to be multiply or divide. Probably divide. Divide by whatever the coefficient of x is here. If it was x over 20, then you will multiply by whatever is in your denominator there. That's how you get a 1. Divide by 20, divide by 20. So now I got 1x is 5 again. 5 is the magic number tonight. Last step. So now you got x. Plug that in. Let's get rid of some of this nonsense. Nine times 5 is 45, minus 5 is 40. 4 times 5 is 20. 7 times 5 is 35, minus another 5. What did I say? 35? 30. 40 plus 20 plus 30, is that 90? Yes. That's what you're looking for. I know my scribble scrabble is hard to read. So complementary and supplementary are like strings of adjacent angles. Maybe just one pair of adjacent angles. Could be a whole bunch of them. Kind of just depends. Not all adjacent angles are special. They don't all add up to net, right? If I would have had just these two right here, and it didn't have that little, like, I can't do anything. They have to tell you something like, oh, this whole piece is whatever, and then you could do something. But if it's complementary or supplementary, Then you can have this whole string of them. If you have vertical angles, then you're probably talking about not two rays coming together, but these two lines intersecting. When you have that, you actually create two pairs of congruent angles. So in geometry, equal is congruent. If you go through the bow tie, those are the ones that are congruent. So this one right here and this one right here, they're the same. Make this a little bit smaller. This one right here and this one right here, they're the same angle. So if you know one, you really know all of them. Because if I have this, let's see, what color can I make you a different color? I know that this right here is a line. So if I just kind of ignore this thing for a second down here, if I can get a shape in, insert shape, boop. Like if I just ignore this little bottom piece for a second, and make this like this, pretend he's not there, and kind of tilt my head, I go, oh, I got supplementary angles. That's a line. This is 40 degrees. They're adjacent angles. Right, here's my line. I got this piece popping out. It shares an egg point. This is 40. I know that this one plus this one has to be 180. This one has to be 40 degrees, 140 degrees, because 140 plus 40 equal 180. Lines are straight angles. They add up to 180. Oh, okay, so that one's done. If I take this handy dan, oops, too far, and I give him a little twisty, and now I'm only looking at this line, that's 140. Well, this is a line now, right? This piece right here. That has to add up to 180. Well, that's 140, so that has to be 40. That leaves me with this last one. One more spin. Whoops, grabbed the wrong rando shape. I have this red line again, but now I'm looking underneath. Well, if that's 40, that has to be 140 because that's got to add up to 180. And so what you have is two sets of congruent angles. That if you go through the bow tie, these two are going to be equal. I got way too much stuff on here. These two are going to be equal going this way. And then through the other end, if you scoot through the little hole to the other side, that's going to be equal. So if you know one, you know them all for your little bow ties. So if I know and it's not going to be drawn to scale, but let's say that this is 75. If I know that's 75, I know that's 75. And then these two are 180, so that's got to be 105, and this is a vertical angle with this, so that has to be 105. That's just the way it goes. All right, so you have that there. You can use this with different, oops, let me grab my image, with applications too. So what I really have here is a set of vertical angles, right? I got something going this way. Right, here's one. One line, first F. Slideshow, no, draw. Let's go purple, and then I got this one. So there's my two lines. We'll ignore the fact that the street has a width. I know that this is 150 degrees. Well, that means that this has to be 150 degrees because I'm right through that bow tie. And this piece is a line with this angle being a set of two adjacent angles that happen to be supplementary because First Avenue is a line. So if that's 150, this, it's going to be hard to see, has to be 30, which means this piece has to be 30. And it's going to work like that every single time. All right. Questions so far before we look at adding in another line. That will be more exciting. Let's see what we got over here. No, see, we already got all cranked up. So you got these two right here. Let me see if I can grab them. My snipping tool has disappeared somehow. It's like it's opening on a screen. Oh, there it is. Come here. Maximize. I'm trying to. I don't know how we got all the way over there. There we go. Let's take these two lovely items and bring it over here. Okay. So not a great image, but we got it. So we have this one right up here. What does that lovely little box in there mean? How many degrees do you know an angle is when you have the little square? 90, thank you. Yes, 90 degrees, thank you. So these two have to add up to 90. So I got x plus 31 is equal to 90. That's a plus 31. So you say minus 31. That zeroes out. It's only, if you don't see a number there, it's a 1. So I don't need to worry about dividing by 1 because it's done. And then that is a 59. So this is 59 degrees, and that's 31 degrees. Both of those are acute angles, because acute angles are greater than 100, greater than 0, but less than 90. So when you have a right angle, when you have complementary angles, both of them have to be acute, because if one can't be bigger than 90, how are you going to, you can't have a negative angle. And then you can't have one, like you can't have them both be obtuse because now they're too big. So your complementary angles are always going to be made up of a bunch of acute angles. Supplementary can go a couple of different ways. Here there's only 2, and we know that this has to add up to what if they're supplementary? $180. There's not many magic numbers. Yes, thank you. It's 90, 180, or you don't care. Like that's it. So I have plus 147. So I'm going to say minus 147 from both sides. And that gives me a number 33. Yeah. So this little angle right here is 33. Now that's acute, but this one is 147. That's obtuse. Obtuse angles are greater than 90, but less than 180. And when you have supplementary angles, if there's only 2, one's got to be big. One's got to be obtuse and one's got to be small. If you have like a bunch like we had in the beginning where there was like 3 of them stuck together, like, you know, they're like that, then maybe they're all acute. But if there's only 2, one has to be a big one, one's got to be obtuse, and one's got to be acute. All right, so the obtuse, acute, right, and straight. 180, 90, less than 90, greater than 90, but not 180. That's all you have to do. If another line comes along and you have two parallel lines, and then some rude line comes slicing through, that's called the transversal. So I have these two little lines right here. They really should at some point, although it seems like this textbook, they're a little lazy, say to you, oh, by the way, L1 is parallel to line 2. These two lines are parallel. They could also put these little arrows like this to show that they're parallel. And frankly, they should have had lines like this. And then this other thing comes sweeping through. That's the transversal, the slanting one, the one that is not parallel. So the transversal cuts across these two pairs of parallel lines. Now, if it was just the one, we didn't have a parallel line floating around underneath. I need to insert a shape, but I don't know where I found it. There we go. I don't know why it does that. Like it doesn't want to do it the first time, right? If I had something that looked like this, right, it was just these two, then I got vertical lines, right? I got vertical angles. I know 1 and 4 are the same, 2 and 3 are the same. I don't know what they are yet, but I know they're the same because that's the rule. You go through the bow tie, you're the same. Same thing if I only had this piece. 5 and 8 are the same, 6 and 7 are the same. They're congruent, they got the same measure. Because these two lines are parallel, remember parallel lines are going the same way at the same rate. They're the same thing in different spots. If I could maybe make this like this, right? So you see how it got laid up? If I could drag that one down along the transversal, you see how it's the exact same thing? I know it's kind of hard to see. I couldn't find an animation probably for this reason. So 1 and 5 are the same. 2 and 6 are the same. 7 and 3, they're the same. 8 and 4, they're the same. So just like you got two sets of the same vertical angles in different spots. So again, just like with the vertical angles, if I know 1, I knew all 4. Well, now if I know 1, I know all 8. And I kind of just hopscotch back and forth. And there's all kinds of different pairs that are created. So there is alternate interior. So think about what alternate means, right? Zigzag. Interior meaning inside. So I got 3 and 6. Those are alternate interior angles. Opposite sides of the transversal, but inside of those parallel lines. 3 and 6 are alternate interiors. 4 and 5 are alternate interiors. They're equal, right? Because I know that 2 and 3 are the same. That's vertical. 6 and 7 are the same. But if I know 7 is 3, they're the same. That means 2 and 6 have to be the same. And it's transitive property. That means these have to be the same. You got alternate exterior. Other side, opposite sides of the transversal, but on the outside, right? 7 and 2. They're on the outside, opposite sides. If I was going to swing this one back down, it would match up with the 6, but it's kind of like it's almost like instead of a slide, like that middle piece kind of gets cut out and it gets squeezed together. You got corresponding angles. That's the overlap. If you were to smush them together, what would they land on top of? So 1 and 5, 3 and 7, 4 and 8. These are all the ones that have the same measures. So if I know 1, I know them all. If I know that the measure, that's the M, of angle 3 is 120 degrees. Why are you not writing? Here we go. I know that's 120. then I know that this is 120 because they're vertical angles. I know that this is 120 because I can either think of them as a alternate interior for the 3 or corresponding from the 120. I know 6 and 7 have to be the same, but they're vertical angles. I also know that 2 and 7 are alternate exterior angles. And so you can see, you kind of like hopscotch down the board, right? So this one is this one, and then it flip-flops over, and then it does this one. And I also know that these are lines. It says it right here, line 1. So if measure of angle 3, well, now that I have it, I can really use anyone. If I know 2 is now a 120, I know that 1 has to be a 60 because this is a line. And these are supplementary then because they're adjacent angles. And then I just zigzag the other way. If you're 60, 460. These are alternate interior. Or I can think about it as corresponding. And then you're another vertical. And I got everybody. One, and everybody gets labeled. Let's talk about boop, get rid of all this. 4, or number 2. For 40, angle, measure of angle 1 is 40. Well, darn, I thought of the same thing. That means if that's 40, this is 40. And this is alternate interior, so that's 40, even though that doesn't really make sense because it looks like it's an obtuse angle. And that means this is 40. Which means that 2 has to be the 120 because I accidentally picked, oh wait, is a 140. Let's fix that. 140 because these two things right here have to add up to 180. And if that's 40, that has to be 140. Which means this has to be 140, which means this has to be 140, which means this has to be 140. So then you have them all. See, if you can draw your 2 parallel lines, just make 2 lines and go like that. And see if you can come up with all your labels for the number 3 and 4, where angle 7 is a 60. Do that, and then start over again with a new one like I did for number 2, and try for number 4. And I will clear this mess out. All right. So hopefully you're all set. It shouldn't take too long because all of these are only going to have two numbers. So once you find one, then you're good to go. So angle 7 is a 60, and you do it however you want to do it. I like to do all like the ones that are congruent. So I know 7 and 6 are 60, and I know that 3 and 2 are 60. These are vertical, alternate interior, vertical again. But you do however you want to do it. If that's 60, the other one has to be 120 because it's got to add up to 180, right? This one of these, whatever one you're looking at, right? Whatever pair of lines that you want. Then I got a vertical, then I got an alternate interior, then I got another vertical. So those are all 60 and 120. If 4 is a 110, 8 is a 110. Well, 4 is a 110, but not yet, right? If that's 110, then 5 is 110. Then 4 is 110. 1 is 110, which means 2 has to be 70, which means 3 is 70, 6 is 70, 7 is 70. Zigzag your way down. If there was a third line, I wouldn't do that to you, but it would be the same thing. You just keep flip-flopping back and forth. So that's parallel lines. More useful than you might think. And if you scroll down, you'll see you'll have a bunch of those of like, well, which is the other corresponding angle? Corresponding is same spot in the other spot. So that would be a 3, right? 8 and 4. The ones that overlap are corresponding. I think alternate interior and exterior make a little bit more sense. Alternate, opposite sides of the transversal, inside the parallel lines or outside the parallel lines. And that can be however they want. Vertical angles are through the bow tie. So you got a couple of those, kind of just matching them up. I think the last one is finding some angle measurements. Yeah, towards the end are some angle measurements. Like that. Which leads us to the last one for today, which is triangles. So if you were in a geometry class, you would probably spend like 3 weeks just talking about triangles and proofs and stuff like that. So we're not going to get real deep into it. So if you're like looking at it thinking like that, like some of this is silly, it's because we're not going to do any proofs. We're just going to be like, this is how you could prove something. Where if you did geometric proofs, you would write out this whole long list of why with all these different rules. But we're just going to be like, oh, it's congruent because this, this, and this is labeled. So it's more exciting if you really do it. But much like angles can be labeled, like with their degree measure or by the type of degree measure they have, right? Like you can be a 30-degree angle or you can be acute. You can be 124 degrees or you can be obtuse. We can do the same thing with triangles. We can talk about triangles either by their sides, what's going on with their sides, or what's going on with their angles. So if you have an acute triangle, all of the angles are less than 90 degrees. If you're a right triangle, one angle is 90 degrees. And if you're an obtuse, at least one angle in there is only one angle could be obtuse. Why? Because the angles inside a triangle add up to 180 degrees. So you can't have two obtuse because that's too big. Like how do you have 100 and 100? Then they'll make it. But you can have all three be acute, one be a right, one a 90, or one be an obtuse. We can also talk about them with what's going on with their sides. But if you're labeling them using the angles, you can label just the you can label it with like just a like triangle 2 or something like that. Or you would say like triangle ABC, where you have all of them in there. And that order doesn't really matter because the triangles, all of them are vertices. It's a closed shape. It's not open like a ray. So if I have triangle ABC, I could say ABC, I could CAB, I could say BCA, I could say BAC, just walk around the edge. Now the angle, though, is what gets labeled because that's the vertex. So this would be side A. I need more space. So if I had something, let's go with ABC, right? A, B, C. If I look out from A, that's side A. That's C, that's side C. What it opens up, if you imagine like C is opening that door, it's like the projection that would come out of C. So B, if I was shining a light from B out, this would be side B. That's where the light would go. So think about standing in that corner and shooting it a flashlight. What gets where the light lands, that's the side for that angle. Or I could talk about them as the sides. If two of the sides are equal, then they're an isosceles triangle. And so there's a relationship between the sides and the angle. Since the angle is what opens up the door, if two doors open up the same amount, the light that gets, that distance that gets created by the stretch is going to be the same. So if two sides are the same, then the angles across from them have to be the same, right? Because if I'm shining the light here and it goes out and it makes this, and I'm shining the same type of light at the same size out to the same distance, then it's got to make the same thing. And the way that we denote things being the same, for sides we use little dashes. For angles we use one little arch. So it could be that this is the same, or it could be that all of these angles are different angles. Right? This is a 90. We know that you can only have one. Maybe these are the same. Maybe they're not. These definitely can't be. Maybe these two are the same, but maybe they're not. But these have to be the same. So my base angles and what's across from them, that's isosceles. If it's equilateral, then everything's the same. That means this is 60 degrees, this is 60 degrees, this is 60 degrees. The sides you don't know. Because an equilateral triangle could be super big or it could be super small. And the angle could be the same. It's about the distance that you let the light shine. These are all different. So this opens up to the 1. This one opens up to the 2. This one opens up to the 3. So if I know all 3 sides are different, all 3 angles have to be different. If all the sides are the same, all the angles have to be the same. If they're all different, that's scalene. Equilateral, they're all the same. 2 are the same. You can have a right equilateral, right isosceles, but it doesn't have to be. A right just means that there's one right angle. And they all add up to 180. Doesn't matter the type of triangle, all those guys on the inside open up to 180. The only thing that has a special name is the side across from the 90-degree angle. That's a hypotenuse. But we're not doing Pythagorean theorem, so I don't know why they mention that. So if I get a triangle, and it says find the angles, well, we know, just like if it was supplementary and we knew it was a line, like this, we know that this adds up to 180. Well, I know that all of my triangles in here, all my angles have to add up to 180. So I just have to patiently add up all of these fun things. Every triangle, 180. Don't matter the shape, what size, none of that. X plus another x. Remember, if there's no number, that means there's a 1. Plus 3x, that's 5x. I have $17, but I spent $62. Not good. So what's that? Negative 45? Or you could just put 17 minus 62 in your calculator. Equal to 180. This is a subtract 45, so I need to add 45 to both sides. That's how I keep the balance that they're equal. I can't fill in one side without filling out the other side. 5x, 225. Now, I only want 1x, so I got to divide by 5. You divide by the same number, that's 5 divided by 5 is 1. 10 divided by 10 is 1. So 1x is 45. So now, just like what we did with the angles, I got to go around and plug all of this in. So that's a 45. That's nice. This is 45 plus 17, so 62. And that gets me up to 107, so this better be a 73. $45 times 5. Nope, 3. There we go. So 135 and then minus 62. Yep. 73, right? So there's my 3 angles. All the angles are different, so all the sides are different. So this is a scalene triangle if I'm talking about by sides. All of these angles are less than 90. If I'm talking about by angles, this is an acute triangle. You got all that fun stuff right there. Ooh, I went too far. There we go. Do we want to do another one of those? I guess not. If I have 2 triangles and I want to know if they're the same, I have to look at all the markings and then compare the markings. And then certain orders of markings will let me know if they're the same or not. So it seems a little odd, but you have to have the right types of markings to be 100% sure that the leftover stuff that you don't know can't vary. And so I'm going to just skip for a minute. You got 4 ways. You can know all 3 sides. Well, if you know all 3 sides are the same, then they're the same. You could be missing a side, but you got to have the angle in between. So you'd have to have side, angle, side. So like you have to know one whole section, like a clamshell. You can have angle, angle, and then the side that's outside of one of those angles for angle, angle, side. Or you can have the angle, side, angle, so it's like you know the angles and like you only like know the bottom. So we would have to know, let's see if I can draw this on here, all the sides, side, angle, side, angle, angle, side. So it's going to be consecutive going around. Oops. Angle, side, angle. That's what I'm looking for. Here's angle, angle, side. Angle, angle, side. You can't have side, side, angle. Right? You can't have that. These 2 unknown leave too much going on out here. So you don't know what really is happening in there. So for this one that we were looking at, if I kind of like tilt this one, let me see if I can do that. Like if you think about this as the base, right, it helps kind of to highlight it. Then I got these 2 right here, that's angle and angle. One little dot, one little line. This is also one line, so those angles are equal. And then I got both of these sides, they're both the same, so maybe I say this one, and if this one like fell over, that would match up with this. So I have angle, angle, side. So those 2 are equal because this has just got one line and those are both have one little arch. Now, if it said that, that's a no, because now they're different. If this has one dash and that's got two, that means they're not the same length. So if I have something that looks like this, I know that this could be angle, angle, side. I got these two right angles. Let me see if I can I? Let me see if I can cut this up. Picture format, crop to a shape. Close, kind of close enough, I guess, to get it to work, right? So it's this guy right here. So if I give this guy a swing like this, I didn't go all the way. I know I have that, right? That's what that piece is over there. And so that kind of helps figure out the order of who matches up with what. If you can kind of imagine swinging them around. So these two count. Those two match. So that's an angle. And then these both have, this has this piece, and this is saying that it's a 1. So let's just concentrate on this one. So the real question is this piece the same as that? Well, this is where your parallel lines come in. You extended that, and this piece right here was your transversal, poorly drawn transversal. You have this angle, and then this has to be equal to that because they're alternate interior. So if this was 40 degrees, I don't know if that's going to stay on there when I go to move it. Probably not. Right, whatever that is, if I spin it, you see how it would land in the same spot? And because I know that this is a rectangle, although they're talking about it too early and we haven't talked about quadrilaterals yet, I know that those have to be parallel. And then they share this one side. So I have angle, angle, side for that. Let's pull up one from in here. So you got some definitions. It's, you know, define the triangle, lots of those. Find the measurements. So like, if I know that these are equivalent, if that's 28, oh, these are different. I can't say those are equivalent. There we go. This one right here. That matches with this one, right? This one's kind of just tipped over. So that's a side. This angle matches with that one. And then this one matches with that one. So I have side, angle, side. That has to work. Now, if this had a 1, see how this has got like 2 little dashes there? And this also has 2. If this only had a 1, then it wouldn't work because they're not the same measure. And if it seems like this is silly, it's because they're already marked. Here's a shared figure. These two are this. It's almost like it is a kite. That's what it's called. But if you fold it in half, right, the A would land on top of C. So these are the same. Those are the same. This is actually the same line in both. So I got side, side, side. I know all the sides. This kind of came out of nowhere, huh? Because I don't see, oh, that's one more slide. Scaling for similar triangles. So if you're congruent, you're exactly the same. If you're similar, your angles are the same, but your sides are different. So it's like when I grab these things and I drag it, right? It's the same picture, kind of, but one's bigger and one's smaller. Same thing with the triangles. So I have these lovely items. If I take this triangle right here, can I get this? Maybe, I don't know. And I squeeze in a new, oh, let me go back to, I'll just use this. Insert new slide. All right, so here's this thing. If I could take this piece right here, right, see how it overlaps? Hopefully, it may not work perfectly because of not really using the right tools, but like I can kind of drag it. You see how it turns out to be the same thing? Let me make it transparent, right? So that's what it was. And then I'm going to drag it down, and it's pretty much the same thing. It's not dragging perfectly because I'm like not using the right tools to do this, but you get the idea. So that means this 3, I can make it real big, right? And it eats up this extra piece down here, which is a 4, which means this whole big piece on the outside is 7, right? So if I have, that's just 3, this whole piece right here is 7. Let's see if I can draw that. That's pretty good. This whole piece, if I wish it would either be 4 plus y, whatever that is. This is an x. There, that would be, this gets scaled up here. So this 7 is to the x the same way that this 3 is to the 2. Right? I make the 3 big, it becomes a 7. Where are you, little thing? Right, there's my 3. Make it real big, it becomes a 7. My 2, I make it real big, it becomes an x. So 3 turns into 7, and 2 turns into x. There's a couple of different ways you can write it. So let's write it that way, because I think that's probably the way it makes the most sense. 3 turns into 7. My 2 turns into an x. This is written so it's side to side. That matters. Right? So little side, 3, turns into big side, which is 7. Little side, 2, turns into big side, which turns into x, right? So little triangle to big triangle, side to side. So these are little triangle up top, big triangle down here, with like sides going this way. If you flip-flop the order, if like you go big to, if you go small to big and then big to small, it's not going to work. So you got to go small to big, side to side. You know, like that flip-flop's got to be the same. This is called a proportion. We've solved these before, way back in 7 or chapter 6. 3 to 7, 2 to x is a proportion. Cross multiply and divide. Remember that? 3x, 14. Divide both sides by, unfortunately, a 3. Ooh. And whatever 14 divided by 3 is. Let's find out. 14 divided by 3. 4.7 when I round. So x is 4.7. If I want to know why, like letter y, not why am I making you do this. Let me get rid of this. Although you may be wondering that as well. Similar figures is just proportions in geometry. It's the same thing, right? So here, I got little side 4. When I drag it, it becomes whatever 4 plus y is, right? See it? 4 goes to 4 plus y, eats up that whole thing. I know that this side is 7 because I got a 3 and it becomes a 7. So I know that 3, again, becomes a 7. And 4 becomes, well, I don't know, whatever 4 plus y is. Because it's this whole side, right? This becomes this whole side, so this has to become that whole side. So now I need to solve this lovely thing. 3 over 7, 4 over 4 plus y. So this is a little sneaky because 3 times both of these, 3 times 4, 3 times y. Can't just hit the 12. 28, right? So still cross multiply. Now we got a little bit more action. If you don't see a sign, it's a plus, so subtract 12 from both sides. 16. Yeah. And another weird number. Divide both sides by 3. 5 point something. Oops. 16 divided by 3. 5.3 repeating. So probably 5.3. So get your y, and I forget what x was already. 4 point something, 4.7 maybe. So that's how those kind of the things work.
I'm on the same problem.
Mm-hmm.
And I got that answer and I already put it in and it didn't like it.
Didn't like it? Oh, round to the nearest 10th. Why? Oh. Because it has to be just y. Ooh, they got us.
Yeah,
Y is 5. Well, y is 5.3.
that's why I got 5 being 5.3. If you add them both together, it would be 9.3.
Right.
I
know what the problem is.
I'm going to be honest, I solved things, so I put 4 and got it right. But I don't know why it's 4.
That's cool. No, because it's wrong. Because it's wrong. That's why. 5 is 5.3. We're not going crazy. If I wanted to know the length of the whole side, that would be 9.3 for reasons that has to be for reasons we don't talk about. So I just have to override that question for everybody. I'll just add 1 to everybody because there's an error in that. Well, we've only found what 2 or 3 errors all semester. That's pretty good for freeware.
Well, when I first did this, it really confused me. I just gave up.
You're like, wait a minute.
So I got 5.3, and then somehow, after trying a different way, I got 5.6. So after I tried that, I just gave up.
Oh, it might have just been a division, like a multiplication thing. That happens sometimes. All right, I know that we're kind of coming close to the end here because we got 3 whole minutes, but I just want to do this one too for you because I felt like I feel bad that the one we did had an error in it. We want to find A and T. This one's a little bit easier because I can like a little bit easier say big to small, right? So here is side A. Let's find that first. A matches up with the 14. So A goes to, that looks like a 9. A goes to the 14. Now, which means I got to go from here to the other side. The only one that's not missing is 6 to the 12. I could say A to 6, 14 to 12. Like there's a bunch of different ways that you could write it. But if you go side to side, then you got to, like, I can't say 12 to 6 going backwards. Big, small to big, small to big. Where these are the sides that line up. You see, like, this side goes to this side, big to small, and then this one went big to small. 12A times 4, carry the 2, 84. So A is 7. Now we got to find T. Now you found A. You could use that one. I would not recommend it. Why? This one probably wouldn't be a problem, but if you had to round somewhere, that rounding can compound and kind of be a problem. This didn't have to round, so it's probably fine. I always go back to the thing they gave me. So if I want to find T, I would start with, 10 to T, but I wouldn't use the A. I know we know what that is. I would go back 6 to 12. This one, there's no rounding. It wouldn't be a problem, but, Cross multiply, 120 is equal to 6T, so T is a 20. These are nice because you can kind of say, times 2 times 2, right? Like, that it's kind of got, this is double that down there, so it had to be double that times there. But you only see those things after you do a whole lot of them, and so it's not a helpful trick in the beginning. So that's the first 3. 1, 2, and 3. No lab this week. I'm going to push it the next week. Make your life a little bit easier this week. Let this settle a little bit. Next week is also area and volume, which is going to be like stuff that's a little bit more familiar than probably this stuff. I'm going to end the recording, maybe, if I can find the thing.